reactivity. But today, we're going to be talking about ionization energy and atomic radius. Let's begin. So atomic radius is the distance from the atom's nucleus to electron cloud. It's standardized by measuring the distance between the nuclei of two identical atoms bonded together. The result is the atomic radius equals half the distance between the nuclei of identical atoms bonded together. Now, the size of an atom is affected by the attraction of the protons in the nucleus have towards the electron cloud and the number of energy levels, also known as N, that the atom has. Now, when deciding which atom is bigger, energy levels always win. So while moving across the period, as a general rule of thumb, the atoms become smaller. So across the period, an atomic radius decreases and becomes smaller. This is because since the atom has more protons, the nucleus has a greater attraction towards the electrons, so the electron cloud is pulled closer to the nucleus. This results in a smaller atomic radius. Now, atomic radius down the family, that's this way, radius becomes larger. Why, you may ask? With the addition of energy levels N, the distance from the nucleus to the valence electrons increases, so the nucleus has a weaker attraction for the electrons. This results in a larger atom. Let's move on to ionization energy. So ionization energy is the energy required to remove an electron from a single atom in the gas phase. It requires input energy, which means that it is endothermic. The more electrons removed is the more energy that you're going to have to use. And to remove an electron closer to the nucleus also needs more energy. Now let's go to the tube. So across the period, ionization energy increases. It becomes more difficult to remove an electron and takes more energy to remove the electron. Why? Because since the atom has more protons, the atom holds the electrons more tightly, causing it to take more energy to remove the electron. This ends up with an increase in ionization energy. However, there are exceptions to this trend. The first set of exceptions is Be, beryllium, versus boron. So B's electron comes from the s orbital, beryllium's electron comes from the s orbital, and B's electron comes from the p orbital. Why is this an exception? Because p orbitals are less tightly held because they do not penetrate the electron cloud towards the nucleus as well as s orbitals. S orbitals are more tightly held because they do penetrate the nucleus more than P, D, and F sublevels. What's the result? It takes less energy to remove the electron from B than it does from BE. The other exception is nitrogen versus oxygen. So two electrons in O's 2p orbital are paired, and N's electrons in the 2p orbital are not paired. Why does this cause an exception? The pair of electrons increases repulsion between the two electrons, which lowers the amount of energy to remove an electron from the 2p orbital of oxygen. The result, it takes less energy to remove an electron from O than it does from N. This can be represented with a graph where ionization energy is the y-axis and the atomic number is the x-axis. So B, beryllium versus boron, would be an S2p1 glitch. The p orbital is less penetrating. Nitrogen versus oxygen would be a p4 glitch. Added electron to electron repulsion. Now moving to down the period. Ionization energy decreases when moving down the period, so it becomes less difficult to remove the electron and it takes less energy to remove it. Why? Since the distance between the nucleus and valence electrons has increased, the atoms hold the electrons more loosely because the nucleus has lower attraction for electrons, so less energy is needed to remove an electron. That's it. Bye.